and well, this Ladyada Mario Kart edition.
Hey, everybody. Which funny, we actually saw a Mario Kart on the street today.
Yeah, we just got back from the office, and that's our kiddo zipping around.
Yeah, it's a remote control, so she has a driver's license.
Yeah, that's what we'll tell everybody.
Yeah. Okay, so it's me, Ladyada. I'm here at my desk, working on some hardware. So this week, the hardware you can see on my screen that came in to get put together is the Bus Pirate RP2040 version, which maybe call Circuit Python, maybe Bit Blast, or I don't know. We're going to call it something. We don't know exactly what yet. I'm calling it Circuit Pirate for now, but it name might change. I just need to, have something for the folder name. So let's go to the computer real fast, and I'll just go do a quick overview because it's been.
Actually, one
Okay.
quick
Oh,
thing.
yeah, sorry.
We had yeah, we're running a little bit behind tonight. Sorry, everybody. We had a visitor, Eric Camp from Seed Studio stopped by. Also, Zach from Particle. We're starting to do things more and more. So, thanks for visiting. And we have maybe some surprises and some collabs that we're going to be doing with Seed soon. Anyways,
Yeah.
back to the show.
I forgot.
Back to your computer.
You thought I'm wearing the same shirt as yesterday.
Yeah.
Okay, so back to my computer. So this is the Bus Pirate, which is this open source public domain board. You can see here had a mini USB, FTDI chip, PIC chip, and it had this little like jumper cable out here that you could connect to all sorts of chips and modules and things to do interfacing with the buses. So we stocked it, and now it's unavailable. So this is the latest, the 3.6, the latest version. It's got this. You can see here the header with the labels for all the pins. It's got these LEDs, power to let you know it was powered, USB like data transfer mode, and then wait, this is upside down. Why is this upside down? Weird. Mode, and then the regulators, because there's two regulators output. Which is one of the things I really liked about this design is it had these regulators that 3-volt and 5-volt output, and the enable pin was tied to a microcontroller pin, so you could disable and enable the output power pins, which were over here. Auxiliary, and then it had SPI, but you could also do, in addition to SPI, you could also do I2C and analog digital inputs. And what's really cool is it was a completely public domain, a Creative Commons 0, which is really cool. Unfortunately unavailable, and I think probably because of the chip shortage got discontinued. So we had a run at maybe revising it, updating it, and using the RP2040, which is not a full drop-in compatible chip, but maybe it can do a lot of the things necessary. So let's go to the overhead real fast. So this is the one I'll show. This is the demo. So this is the board. I thought I would just point out some of the things here, and then I realized I don't have something to point with. Let's see. Grab a pen. So let me do an autofocus lock. Okay, so the RP2040 chip, and then this is the 8 megabytes of SPI flash. 8 megabytes is a ton. We don't need that much, but maybe if you're programming a chip, you have the firmware on the flash and that like in the file system, and you can have a standalone programmer. We talked about this. This is the analog switch, which is used to connect and disconnect the external pull-up resistors. They had a very interesting technique for interfacing with 5-volt logic, even though even the original Bus Pirate was a 3-volt chip. This is also a 3-volt chip. I added a couple of things like the STEM IQ T-port and a mode switch to connect between. There's a couple different, we're going to have different modes for use. Like if you want to have it run CircuitPython and have the REPL be available, or maybe hide the REPL and only have the user interface available. The reset button, which you need, always, and then the boot button, which is also a user button. This gets you into the bootloader mode. Added a couple extra LEDs. So we have that standard power LED and the mode LED. I added 2 LEDs, one for each regulator, 3 and 5 volts. And then RX and TX, I thought this could be like activity, maybe. I don't know. The LEDs are really cheap, so I threw them on. NeoPixel down here, but yeah, I was thinking maybe put the NeoPixel up here instead. I don't know. And then a little bit of analog circuitry just to kind of help interface. These are the regulators. So the onboard 3.3, the external 3 and 5. This is a 5-volt fuse, crystal, and then a couple of resistors to keep the USB-C happy. And then that same header that connects. And what's neat is, this is the demo board version. So this is running my little demo. The original Bus Pirate, one of the things that was nice is it came with like a cable set that made it easy to use. And even though the RP2040 is not the same as the PIC chip, totally different families. The PIC is PIC 16, and this is an ARM Cortex M0, and it's got some cool stuff like PIO, which I think would make it very useful, I think, and also Pico Probe, which is the open OCD port. So the RP2040 I think is a really good chip for this core. Sorry, for this project. But there's a couple things that were a little complicated that I'm still kind of working out. So you can see here these diodes. So can you go to the computer real fast, maybe? So the diodes are here, and the idea I had is, the thing that, what's interesting is the original Bus Pirate only needed four ADCs to monitor the two regulators, auxiliary output, so the ADC outputs, and sorry, I'm trying to remember it. So there was the ADC, the external voltage, and the 3-volt and 5-volt power supply. So the fact that the RP2040 only has 4 ADCs actually is totally fine because you only need 4 ADCs. And it definitely has enough GPIO. One thing that's a little annoying is, the pin muxing is identical, but, you can mimic I2C very easily. It doesn't have open drain connections, but you can also mimic open drain by like switching from output to input and then using these external pull-ups. But the thing that was a little challenging was the PIC 16 that the Bus Pirate used was 5-volt friendly. Like it could accept 5-volt signals even though it was running at 3.3 volts. It's just something about that chip. Some chips can do this. I know the STM F103, I think, very popular chip, has some pins that are also 5-volt compliant. And so you can use that to interface, like some people use it to interface with like SCSI or something, which is a 5-volt protocol, even though you're running on a 3.3-volt microcontroller. The RP2040 is a 3-volt chip, and it didn't say 5-volt compliant. And so one of the hacks that I do often, and I was like, well, I was in a rush to kind of get this out, and I was like, well, I don't think it's going to work, but I just popped it on anyways, is what's called like a Zener clamp. And so if these signals go through a 1K resistor, and then they have a 3.6-volt Zener diode reverse connected. So if this voltage, let's say this SDA 0 pin goes to 5 volts, this Zener will hit 3.6, actually, plus or minus 10%. That's why I use 3.6, not 3.3, because, I want to get a little bit of room either direction. It'll hit 3.6 volts and like turn on and clamp this voltage at 3.6, and then you'll lose that 5 minus 3.6, the 1.5 volts across the 1K resistor. 1.5 milliamps will get drawn from the 5-volt supply, the digital output, and it'll clamp the voltage. And I've used these voltage clamps all the time. They're also good for like reverse, voltaging. If this goes below 0 volts, this will also clamp the other direction. So it's, these are like a very inexpensive, they're 2 cents a piece, inexpensive way to limit the voltage. And this would work great if this was digital IO and this input was 5 volts. Again, as long as the thing that's pushing 5 volts in can supply 1.5 milliamps, you're good to go. Problem is, I forgot, we're not accepting 5 volts in as a digital, like you may get a 5-volt logic level input from like a CMOS push-pull output, but for the most part, we're probably going to be using this pull-up kit here, where we use the 4066 to pull up those voltages. And here I actually kind of messed around with this and made this 1K, but this is actually, because I was kind of messing around. These are all 10K pull-ups. They're very weak pull-ups because they're meant to work with I2C, or I think SWD maybe also is open drain. So this doesn't work because when this pull-up is enabled, you've got a 10K, from V external might be 5 volts through the 10K resistor and then through this 1K resistor. You're not going to be able to get 1.5 milliamps because you've got that 10K resistor that's acting as your choke. So this Zener diode needs a fair bit of current to kind of activate, and without that, it kind of floats at a lower voltage. It doesn't clamp at 3.6. It clamps a little bit lower. So it doesn't work very well with pull-ups. I should have remembered, like, oh, right, I'm using pull-up resistors. But hey, that's why we do board spins. We learn from our mistakes and we do more. So I was kind of like, oh, what am I gonna do? Like, it's not easy to have a digital input be protected against 5 volts and also be able to have, there's a lot of chips that do level shifting bidirectionally, right? Because you want bidirectional and open drain support. The TXS 0104 can do open drain. The TXB 0104 can do digital, but they can't do each. You can't do both. And I want it to work with both SPI and I squared C and one wire and like who knows what else protocols. So I was kind of like, what do I have to give up, right? Because I'm in trade-off land. And then like oddly enough, I was kind of like Googling for something different, and I bumped into this article that linked to a post from Evan from the Raspberry Pi Foundation. It's like this project that does some PCMCA thing, and they're like, well, it's 5 volts, but like they just plugged it in and just said, hey, whatever, like let's just blast 5 volts into there. And Eben said, actually, um, even though it's not documented, the pads are 5 volt tolerant, just not 5.5 volt tolerant, which means that there's enough input, current limiting and diode protection to keep. Just if you just put 5 volts in, you'll be fine, but 5.5, it's not guaranteed. Also, it's not a bad idea not to guarantee this because people just like be like, oh, I connected 6 volts in. Why didn't it work? Right? Because you can have, plus or minus couple point X volts. There's a really good app note from Microchip, and it's just called like just like tips and tricks, 3 volt tips and tricks. And they had a whole mess load of different ways of doing level shifting. And what's cool is they had a bunch of like Zener diode stuff too. It's like, hey, you want to make like a really cheap 3 volt regulator, use a Zener diode. I love Zener diodes. They're great. They also do a lot of 3 to 5 volt level shifting, and I've used a bunch of these tricks to do this. Diode offset, I've done this before. Voltage comparators, plus or minuses, and then don't forget, again, inside of every microcontroller, well, almost every microcontroller, the once in a while, again, they might not have this double diode protection. There's these clamping diodes that, you can kind of sort of mostly get away as long as this R serial, this like choke resistor, at least if it's high enough. The only problem is that this resistor and this capacitor form an RC filter, and so it'll slow down high-speed signals. But as long as you don't have enough current that will blow out this diode, and like the diode is not going to be like a power, it's not a 1 watt diode, it's going to be, who knows, maybe 10 milliwatts, 100 milliwatts or something. You can dissipate that current and you can have 5 volt inputs. And there's a couple other options. So I might look at, one thing is I'm thinking if it's already 5 volt compliant, what I might do is just keep that 1K resistor, and maybe I'll email, the RP2040 folks, just be like, hey, can you tell me the wattage of this diode, and just make sure I'm well below that. Another thing is though, when you have this current going in here, this 5 volts minus 3 volts, so this is 1.5 volts across this R SIR, whatever that current is going to be injected into VDD, and so your VDD will start rising a little bit. And I've seen this, there's boards that are like, hey, yeah, like the inputs are 5 volt compliant, but when you power it from 3.3 volts and you put 5 volt signals into the pins, the VDD starts floating up higher and higher. And, maybe like 1 or 2 IO pins, it floats up to 3.4, 3.5. But before you know it, you have a couple of IO pins being fed 5 volts, it starts to float up to 4 volts. So, and then like now your chip may be out of spec because it's not spec to have the VDD that high. So, things to watch out for. You can also, of course, have an external clamping diode, and then you set the wattage. You're like, hey, make it as big as you want. And they have another option here where this, they talk about the diode clamp, a cheap way to do it. But if you want, you can use this transistor clamp. I've never done this trick, so I think this might be interesting. I might check that out. Okay, so that's where I'm at with the bus pirate. I did write a quick hardware test. I love doing this because it's just a fun way of verifying all my hardware capabilities. So like setting up the NeoPixel, and you saw it floating around. And then let's see, I can run this test. So I just have a very basic test that scans the I2C, and maybe I'll plug something in real fast so you can see it change. And then we'll move on to so now you can see that the secondary I2C finds the 70 address, and then remember that internal ADC measures the 3 and 5 volt external voltages, and it just verify that it works fine. It works fine. So I'm still going to be able to use this hardware. I can just remove those Zener diodes and just start playing around with this hardware. And I'll do a revision maybe with those other clamp techniques. But it's tough because it's very easy to shift if you're just doing I2C or SPI or one wire, like only one of these protocols. Oh yeah, there's like a really easy way to do level shifting or level protection. But if you're trying to support all of them, and 1.8 volts, things get a little bit weird and funky. Anyways, so that's where I'm at. Okay, so let's get on to the great search.
Where in the world is that part I need? The great search with Digikey.
The Great Search brought to you by Digikey and Adafruit every single week. Ladyada user powered engineer to help you. Yes, you find the things that you want at digikey.com. Ladyada, what is a great search of the week this week?
This week we're looking at Zener diodes. So let's go to the computer and I'll show my moment of Zener. So Zener diodes are great for a bazillion things. One of the projects that I've been working on is this protocol interface that is supposed to be 5 volt compliant. And one of the ways I'm doing that is using this Zener clamp to make sure that the inputs coming into these GPIO pins never really get above 3.3, 3.6 volts. And I've realized, people don't realize how amazingly wonderful Zener diodes are. They're great. They're wonderful. I mean, they're a dessert topping and a floor wax. Some fun tips can be found in this document. It's just called like 3 volt tips and tricks. And the particular technique that I mentioned, there's actually a couple in here. So one is using a Zener as a very low cost regulator or power supply, or like whenever you need a voltage reference, plus minus 10 volts. It's not precision, but sometimes it's okay. Sometimes you're just like, look, I just need about 3 volt input to bias something. You just need a resistor and current going into the Zener diode. And this will kind of sit at whatever, this is rated as the 3.6 volt Zener. This will be at around 3.6 volts. So that's a Zener power supply, and there's a couple notes about it. A Zener clamp, that's the voltage protection circuit that I mentioned before. The voltage going into here, as long as this resistor makes the bias into D1 about 5 milliamps or so, or less. Yeah, we're like 5 milliamps. I mean, it's not, depending on the wattage. This V out won't exceed the reverse voltage of the Zener diode. There's also a great tutorial by Evil Mad Scientist. It's over 10 years old, but Zener diodes never go out of style. So check it out. Introduction to Zener diodes by EMSL, wonderful scientists over in California. And they talk about all the different tips and tricks that they use Zeners for. Again, like simple voltage regulators, level shifters, making, stacking them up to make multiple reference outputs from a higher voltage supply, because they'll have that positive, they act like a normal diode when forward biased with like a 0.7 volt drop, but on the reverse bias, they can have an adjustable drop. And so when you purchase the Zener diode, you'll have to specify what the reverse voltage breakdown voltage you want is. And we'll show that more tips and tricks. Here's a fun one. You know, they use this to drop a 36 volt input into a 5 volt regulator. They just need to like lose 10, 12 volts. A 12 volt Zener will do it as long as it's rated for the amount of current and then the voltage drop across it. So that's something to watch for. Zener diodes, let's go to Digikey and check what they've got. First off, you might be wondering, am I at the Digikey site? Because the logo looks different. They just did a logo refresh. They're going with a brighter red color, which I like, and they're losing the dash in the Digikey. I think they did a post on social media also about their rebranding. I like it. It's a little bit more modern. I personally think that the D, like the D in the center of the D, like reminds me of the catalog sitting on my shelf for, you know, decades. Maybe that's what the D stands for. So they've got Zener diodes. Do they ever? Hundreds of thousands of them almost. So there's Zener kits. And there's Zener diode arrays, but I'm going to look for the single Zener diodes. Looking for, you know, active ones, in stock, not marketplace. So that gives us down to, you know, 9,000. So the reverse voltage. So there's a couple of standard voltages. There's a few, you know, families that are popular. I tend to use the MM series. It's made by, you know, they're made by multiple different manufacturers, and they come in kind of set voltages like every 0.3 volts. So it's like 1.8, 2.1, 2.4, 2.7, 3.0, 3.3, 3.6, et cetera, et cetera. They go very, very high, but for what I often am using Zeners for, which is again clamping a signal down from say 5 volts down to 3.3 volts, I like to use a 3.6 volt Zener. Now you might be wondering, why aren't you using a 3.3 volt? Because oftentimes I'm not biasing with a full 5 milliamps, and most of them are rated, that voltage that they're rated at, the nominal voltage, you only get when you're putting a significant amount of current through. But if I'm connecting this up to some other digital signal, I'm not usually getting a full 5 milliamps. In fact, this 1K resistor is limiting me to you know, 1.5 volts across, 1.5 milliamps through the 1K resistor. So this is going to be, you know, 1.5 milliamps. I've measured it. It never quite gets to 3.6. It's usually like 3.2, 3.3. So let's look at, again, but you can get any voltage you could possibly want, including 3.3. So let's look at 3.6 volt Zener, and then I'm going to do surface mount because personally I'm going to be using surface mount, but they have through hole. You know, it's one thing you can definitely get through hole forever, are Zener diodes. And basically you can get, you know, any package you like. And the thing you're going to want to watch for is, oh wait, did I click 3.3? Sorry, I meant 3.6. So let me delete the nominal voltage and then go back, and I'm going to select nominal 3.6. That's what I meant. Apply, and then don't forget, you always have to have, you know, Zener diodes, they only work when there is a resistor. You always have to have a resistor to limit the current and the voltage that's going to appear at the so that this reverse voltage has, there's some, the Zener diode has like a 3.6 volt reverse voltage. If you try to put full 5 volts directly on it, it doesn't like regulate it. It'll try to pass all that voltage through. It'll draw a lot of current and it'll blow up. So you need to have, much like an LED needs a choke resistor, you do need to calculate your choke resistor. How do you calculate it? It depends on the milliwattage of the diode. So you have to figure out, with that voltage drop across the reverse biased Zener, 3.3, 3.6, and how much current is going through it, you can't go above the milliwattage. So it's a trade-off, right? If you're trying to drop a huge amount of voltage with a lot of current, you're gonna have to go big. So these tiny SOD 323s, you know, good for those little 1.5 to 5 milliamps, little signal level shifters. If you're trying to use it in a power supply, like we showed with the evil mad scientist example of using it to drop voltage into a regulator, you're going to need something much bigger. You'll need like a 1 watt or a 2 watt Zener, and they make them in those wattage, but you might have to go with through hole to get that physical size. Or you could always, you know, use multiple ones. This one looks like you know, it's chunky. It's a DO 219AB, 800 milliwatts. You can get them in, you know, you can look up here for the Power Max. You can get them up to like a watt or 1.5. But again, we're doing it for signal. We don't really care. And I do like the SOD 323. I want it to be nice and compact. So I'm going to pick that for the size. The rest, the 123s are a little bit bigger. I want to kind of minimize space. And you know, there's a lot, but this one's a really, you know, 2.5 cents on semi. So I know that they're gonna be able to always have them in stock. Not zoom in. Come and tape in reel, and then, you know, look at the data sheet for specification. I will say that they're jelly bean parts. The MM3Z series, you know, they're available from multiple vendors. They'll just have that different 3V6 where the XXX is in the data sheet. You'll get different voltages from 2.4 to 775 volts. But still not a bad idea to look, especially if there's an impedance and what current it's expected. Again, 5 milliamps is pretty common. That's a good idea to look. And the variation, you will get variation. So the 3V6, like I said, can go as low as 3.4 to 3.8 at 5 milliamps. But I don't usually drive them at that current, usually drive them at a lower one. It looks like once you get to the higher voltages, they're expected to be driven at 2 milliamps instead. So Zener diodes, they're amazing. Really, they do everything. I love to throw them into my designs for all sorts of like random voltage reference protection circuitry. And they're really cheap, 2 cents. So check out some of those links. We'll have them in the description so you can read the Evil Mad Scientist guide, as well as the microchipped 3-volt tips and tricks PDF for these wonderful Zener diodes.
Where in the world is that part I need? The great search with Digikey.
And that's our show for the week this week. Thank you so much, everyone, for joining us. Get a little glimpse of what we're up to and more. We'll be online all week doing tons of cool things, tons of cool projects.
Beep, beep.
You'll see lots of factory footage, new products. We got show and tell. We got Ask an Engineer. We got everything going on this week and more. We'll see everybody later.
Thanks, everybody.